Here we're going to start looking at the reactivity of amines, starting with a reaction that we've seen in the context of nucleophilic acyl substitution and aromatic synthesis of substituted benzenes, acylation of the amino nitrogen. So this is an example of a nucleophilic substitution reaction in which the nitrogen, the amino nitrogen, acts as a nucleophile and displaces a leaving group connected to a carbonyl carbon, and this establishes an amide. So acyl chlorides, for example, can be used for this, or anhydrides. And anhydrides generally work great, and you'll commonly see this. So, for example, recall that if we tried to do Friedel-Crafts acylation with aniline, aniline is a very electron-rich aromatic compound, and the nitrogen is quite basic, Lewis basic and Bronsted basic. So when we combine the Lewis basic nitrogen of aniline with the Lewis acidic AlCl3, we'll see no reaction whatsoever. We won't even see acylation of that amino nitrogen, and we certainly won't see the Friedel-Crafts product, which would be this. Instead, we'll get a Lewis acid-base complex between the amino nitrogen and the Lewis acidic aluminum center. To get around this, we really need to tame the basicity, lower the basicity of that lone pair on nitrogen. And this can be done through acylation. And of course, this works for alkylamines as well in cases when the nitrogen's basicity is problematic. So you can actually think of the carbonyl group as a kind of protecting group for amines, protecting that amino nitrogen from acting as a Bronsted base under strongly Lewis or Bronsted acidic conditions. So to get around this, we can acylate the nitrogen using something like acetic anhydride and pyridine is the example I've shown here. You could also hypothetically just use an acyl chloride for this with another equivalent of base to sort of siphon off the HCl. And then we can run the Friedel-Crafts reaction, installing the acetyl group or acyl group more generally. And notice that the acyl amino group right here is still an ortho para director, so the acyl group is installed para or ortho to that group. And then in the third step, acidic hydrolysis with heating converts the amide back to an amine, back to NH2. So the acyl group is removed and replaced essentially with a proton there to give the sort of unprotected or revealed or unmasked amino group. So notice the overall result is what we wanted to do over here, but it requires protection as an amide, then running the Friedel-Crafts reaction, and then deprotection with acidic hydrolysis at high temperature. N-phenylamides are generally much less reactive in electrophilic aromatic substitutions than anilines themselves, so protecting as an amide prevents overreaction. For example, if you just take aniline and treat with Br2, even in the absence of a Lewis acidic catalyst, you get tribromination at the ortho and para positions with respect to the amino group. However, for the amide, for the corresponding N-acetyl aniline, where now this nitrogen is a lot less Lewis basic, you have to go back to using a Lewis acidic catalyst such as FeBr3, and this gives only the monobromo product, only, for example, the para-bromo aniline product after deprotection or hydrolysis of the amide back to an amino group. So this conversion of the strongly donating NH2, or more generally alkylamino group, to a much more weakly donating acyl amino group moderates the reactivity of the aromatic ring, but still allows us ortho-para directing properties in that substituent. So this is a really nice reaction in the context of aromatic synthesis. The Hofmann elimination is an elimination of quaternary ammonium salts that gives alkenes. We already know how to do this using alcohols, and this is a useful analogy to draw, and so it's a useful starting point for talking about Hofmann elimination. If you take an alcohol and you put it in strong acid, for example, H2SO4, this can lead to protonation of the alcohol oxygen. That's a basic oxygen atom, right? Bronsted basic. And then water in the reaction mixture can deprotonate beta to that OH2 plus group, kicking off water and giving an alkene product. So given that we already know how to do this using alcohols, what's the point of learning this with amines is a question you may have. We're going to answer that question here shortly. But first, I want to show you the basic idea of how the Hofmann elimination works. The Hofmann elimination takes advantage of the potential idea that a ammonium group could act like a leaving group in the same way an OH2 plus group can act as a leaving group. This is not as good of a leaving group, right? Because N is less electronegative than oxygen, so it's less inclined to take a pair of electrons with it and depart. But we can at least try. right? And the conditions of the Hofmann elimination manage to achieve this. So we start with some alkyl amine, typically with a primary amine with an NH2 group, and we treat with an excess of an alkyl halide. And since we're going to throw away these alkyl groups that we're installing, ultimately we can use a very simple alkyl halide like methyl iodide. It's also important for this not to have beta hydrogens, otherwise you might get competitive elimination within these alkyl groups that we're installing. So we treat with an excess of a methyl halide, methyl iodide, methyl bromide, methyl chloride, and the excess is used to make sure we go all the way to the quaternary ammonium iodide salt in this case. So we get 3 alkylations, sort of SN2 times 3 at that nitrogen, right? And 3 losses of 3 protons to make the quaternary ammonium cation there. And then we treat with silver oxide, Ag2O, under aqueous conditions at high temperature. And the high temperature just encourages elimination, encourages the loss of the trimethylamine group as a leaving group. So what's going on here? What's up with the silver oxide and the water? Well, silver actually combines with the iodide anion to form an insoluble salt, silver iodide, and this leaves behind the highly basic oxide anion O2-. The O2- can react with water in a proton transfer process to give 2 equivalents of hydroxide, and this is, of course, a base. So hydroxide base is generated under these reaction conditions, and the use of silver is convenient because this precipitates iodide from the reaction mixture, in essence replacing the iodide anion, which is not basic at all, with the hydroxide anion, which is a great base for this purpose. Hydroxide comes in and deprotonates at a beta carbon relative to the position of the trimethylammonium group. So notice, here's our trimethylammonium group, alpha, beta carbon. Deprotonation occurs there with loss of the leaving group, so we can draw this as sort of an E2 type elimination. And this, too, establishes an alkene. So notice, the product is exactly the same. The only difference here, really, is that the byproduct in the second case is not water, but is trimethylamine. Notice in the top case here, we can think of water as a byproduct, since that's what left with a pair of electrons. Here, trimethylamine is serving in that role. This is the basic idea behind the Hofmann elimination. On the next slide, we'll see why this reaction is useful. The Hofmann elimination is useful because it gives alkenes with a substitution pattern that we can't achieve using, for example, acid-catalyzed dehydration of alcohols. It gives anti-Zaitsev alkenes, and we'll see what that means on this slide. Let's imagine we started with an alkylamine starting material like this, in which there are 2 different types of beta hydrogens with respect to the amino group. If we number the carbons, we've got a CH3 group at carbon 1, and that's 1 beta hydrogen. We've got a CH2 group at carbon 3, and that's a different type of beta hydrogen that would lead to a different alkene. So 2 different alkene products are possible. When we run this reaction, what we observe is that the major product is actually the less substituted alkene. Notice that elimination of a hydrogen from carbon 1, a proton really, from carbon 1 has occurred, and this is what we might call the anti-Zaitsev product. This is not the more substituted alkene. The more substituted alkene would be this, right, with the double bond between carbons 2 and 3. What in the world is going on here? Well, to get a handle on this, I want to look at Newman projections associated with the anti-E2 elimination that's going on in this reaction for the 2 orientations that lead to the less substituted and more substituted alkenes. To help us work through this, I've built a model of this amine we've been working with, in fact, the trimethylammonium cation intermediate that undergoes elimination, so we can see the difference between deprotonating at the less substituted methyl carbon, which is right here in this model, and the more substituted, we might say, methylene carbon, CH2, right here, and this is the proton we're going to remove in that case. Let's start with removing the more substituted proton actually at this position, since this is what we would expect based on Zaitsev's rule. Now, this is an E2 elimination. We saw that in the mechanism on the last slide. An E2 elimination requires that the proton that is removed, which is the one right here, is anti to the leaving group, which here is the trimethylammonium group. So the conformation in which elimination occurs is this one right here. And we can notice, for example, that the propyl group, the 3-carbon chain, or really, I guess, 2-carbon chain that I'm holding in my right hand right here, is going to end up trans to the methyl group, which is in my left hand, right, based on this, this conformation. There's an issue with this conformation that we're going to come back to, and actually it's worth pausing and taking a moment to examine this model to see if you can spot the steric issue. There's a destabilizing steric or non-covalent interaction between two of the groups in this conformation that's missing from the other conformation we're about to examine. Let's take a look at that other conformation now. So now let's imagine we're deprotonating not at the methylene, but at this methyl group here. So now this proton is the one that's going to be removed, and it is indeed, in this conformation, anti to the trimethyl ammonium group. Now we can just remove this proton and eliminate to create a CC double bond. Right here, the trimethyl ammonium group departs. It's now trimethylamine, and we get a double bond. And here, notice that we've got 2 hydrogens on the front carbon, and this hydrogen on the back carbon, and this 3-carbon chain that's in my right hand. And so here the steric situation is actually much better. Let's go back to deprotonating the methylene carbon. One thing we should notice about this conformer is that the propyl group here, or rather the ethyl group, the 2-carbon chain, is gauche to the trimethyl ammonium group. That's a destabilizing situation. This group in my right hand would much rather be anti to the trimethyl ammonium group. However, in that anti-orientation with respect to this 2-carbon chain here, now the proton we want to deprotonate, in fact, both protons are gauche to the leaving group, not anti. So E2 elimination is highly inefficient from this conformer, even though this conformer is the most stable conformer of the molecule. So this tends to disfavor E2 elimination at the more substituted site in Hofmann elimination. And the bulkiness of this trimethyl ammonium group has a lot to do with that, since this is a pretty severe gauche interaction. If the leaving group were bromide or chloride in a more straightforward Zaitsev type E2 elimination of an alkyl halide, this would be much less of an issue. But in the Hofmann elimination, this trimethyl ammonium group is so large that elimination tends to occur from here. And this allows us to avoid that problematic gauche interaction entirely. For example, we can rotate, this group can rotate however it needs. This group can now be anti, and this is a bit subtle to see, but notice now this ethyl fragment is anti to the trimethyl ammonium group, and we can eliminate off the methyl group just fine. So what we can see then on the Newman projections is that in the Newman projection leading to the more substituted alkene, there is necessarily a destabilizing gauche interaction. And it's between the trimethyl ammonium leaving group and this alkyl group on the more substituted end, if you like, of the alkyl amine. That's going to destabilize the transition state, really, leading to the more substituted double bond. So this is sort of a kinetic issue. This elimination is going to be kinetically slow, even though the more substituted alkene is more thermodynamically stable. On the other hand, when we eliminate off the methyl carbon, that gauche interaction is gone entirely. And in fact, carbons 4, 5, and 6, this fragment right here, is now anti to this group right here. And so we're in a great situation here where there is no gauche interaction. So this elimination is quite a bit faster than the elimination to form the more substituted alkene. And this all hinges, again, on the large size of the trimethyl ammonium group. We've seen that amines are pretty good Bronsted and Lewis bases, and when you put an amine in the presence of an oxidizing agent, a source of electrophilic oxygen, the nitrogen in an amine can coordinate to that oxygen to form what's called an N-oxide. Really interesting structure, N-oxides. Here we're going to look at one particular important reaction of N-oxides and talk a little bit about their structure and how they come about. In fact, if you take an amine and just leave it out in the open air, oxidation by O2 and other components of the air can lead to the production of N-oxides. They're a source of decomposition for amines that are just sitting out in open containers. But if we take an oxidizing agent, a deliberate oxidizing agent, like a per-carboxylic acid, like metachloroperbenzoic acid or per-acetic acid, or even something like H2O2, hydrogen peroxide. These are both sources of electrophilic or Lewis acidic oxygen atoms. And the lone pair on the nitrogen of an amine can coordinate to that oxygen atom, creating a structure that looks like this, with a formally negative oxygen atom and formally positive nitrogen atom. And it's worth verifying that that comes from this lone pair being donated to the oxygen so that nitrogen's formal charge increases by 1 and oxygen's formal charge decreases by 1 unit. This is known as an N-oxide. It's oxygen linked to the nitrogen. Because both electrons in the NO bond came from the nitrogen, you'll sometimes see N-oxides drawn in this dative bond form, emphasizing that this is a coordinate covalent bond with both electrons in the NO bond coming from the Lewis basic nitrogen atom. I would say this is a little bit less common than the sort of polar form with N plus and O minus, but this is another way you'll see it, and arguably it's a better representation in the sense that this bond is absolutely dative with both electrons coming from the nitrogen and going to oxygen. N-oxides engage in a number of interesting reactions, and we're going to focus on one on this slide in particular, but just to talk a little bit in general about these reactive intermediates, the O appears nucleophilic, and the polar form really emphasizes that. And you can do things with this O involving the oxygen as a nucleophile. For example, you can acylate it with acetic anhydride or an acyl chloride, or you can connect a sulfonyl group to it by treating with a sulfonyl chloride, or various other electrophiles can form bonds to this oxygen. So it's Lewis basic. It's also somewhat Bronsted basic, and that's a nice segue into the reaction we're going to focus on here, which is known as the Cope elimination. The Cope elimination is a concerted intramolecular elimination reaction of N-oxides in which that oxygen in the N-oxide acts as a Bronsted base to deprotonate at the beta position in an intramolecular way. And it's a syn elimination, which distinguishes it from E2 eliminations, for example, the Hofmann elimination that we just looked at. And that has interesting stereochemical implications and useful stereochemical implications, as we'll see. So the basic idea here is that we go from the N-oxide, which is generated via treatment of the amine with an oxidizing agent. This is most commonly hydrogen peroxide. That works great, although a per acid like MCPBA also works. That produces the N-oxide, and on heating to promote the fragmentation of the N-oxide from one molecule into two, an elimination will take place in which this Lewis basic and Bronsted basic oxygen deprotonates at a beta carbon relative to the position of the N-oxide group. And the C-N bond departs, breaks toward nitrogen, allowing hydroxylamine to depart as a leaving group. And notice also that a CC pi bond is created in this reaction. So it's an elimination that establishes a new alkene in the product as well as a hydroxylamine byproduct. And the reaction is fully intramolecular, and this can be proven with a variety of experiments as well as observations of the stereochemistry of the reaction that we're about to make. And it's syn meaning the leaving group, which here is the positively charged nitrogen, and the acidic hydrogen are in a syn orientation in the reactive transition state. This syn orientation is required to put that acidic hydrogen in the vicinity of the basic oxygen atom. And so this is the transition state for the Cope elimination. Intramolecular proton transfer, formation of a CC pi bond, and cleavage of the CN bond towards nitrogen all occur in a single step. This produces hydroxylamine, dimethyl hydroxylamine, in this case above. That depends on what the amine was initially. Generally, you don't want anything more complicated than two methyl groups on that nitrogen when you're running this reaction to avoid complicating side reactions. And this is the alkene we get. And if we look at the configuration of this alkene as a function of the configurations of these stereocenters in the starting N-oxide, we come to see that this reaction is stereospecific. Groups that start out cis in the transition state end up cis in the product. Groups that start out trans in the transition state end up trans in the product. This is great evidence for the concerted intramolecular nature of the reaction. So here, for example, A and B start out cis in the transition state for syn elimination here. and they end up cis in the product. And this is the only stereoisomer of product observed. We don't observe any of the product in which A and B are trans, in which the D and B groups have switched places, and this is because the reaction occurs in a single elementary step via a concerted pericyclic process like this. If we start with a single diastereomer of an N-oxide, we'll get a single product out, either E or Z, trans or cis, depending on the geometries of these stereocenters in the starting N-oxide.